All right, hello everyone. Welcome back to the HoTTEST Summer School 2022. Today we have the first of the last three lectures on homotopy type theory by Egbert. So congratulations for making it this far. And today Egbert's going to tell us about propositional truncation. So take it away.
Yes, and it's really great to see so many of you participating in the summer school, solving exercises and asking lots of questions. And it's really nice to see all of you, how you're learning this stuff, what you're picking up. And it's really a great experience for us teachers also to do this. So I want to thank you all. Okay, so in my last three lectures, what I'm going to teach you, so what you will learn from me is, okay, so today's lecture will be about propositional truncations. Truncations. Oh, and I should say, if you like to have the already written notes, they are on the GitHub. You can download them. And here I'm just going to write exactly the same notes, but I'm going to write it in front of you. But you can already have notes from GitHub if you want. Okay. And in my second lecture, I'm going to talk about the univalence axiom. And in my third lecture, I'm going to give you some practical applications in the area of univalent combinatorics. Oops, and here the idea will be just to take some examples that everybody usually is familiar with, and see what we can say about them from a univalent perspective. And that will be my last lecture. I'm also going to try to teach you some soft skills, because I want to actually that you guys are learning something. So one of the most important things is that type theory is really a language in which you can be conceptually very precise, and it's even better than set theory to reason about concepts more clearly with much greater clarity. So how to express yourself in type theory. Oops. This will be a very important recurring theme throughout my three lectures starting today. Then let's see how to think carefully about concepts, and getting it right, as you will see today with the propositional truncations, we'll see quite a few examples of concepts that if you would say them using the Curry-Howard interpretation of logic into type theory, then actually you'll get it wrong. And you have to sometimes think carefully about where to insert a propositional truncation. How do you use univalence to get your concepts correct the way they're supposed to be? So this will be one of the big themes for these three lectures. And then the last one let's see where we are here. Also, how can you spot univalence? In your, let's see where we are here, daily life. So, please, sorry, I'll move that up a little bit. Okay, my computer cropped that. Okay. There are quite a few instances, especially in combinatorics, where you wouldn't necessarily expect any new fancy axiom that has mostly a homotopical nature to have any impact, and still univalence is all around. So that's also what we're going to learn in these 3 lectures. Okay, so with this out of the way, I'm gonna properly start the lecture. Let's see if we can scroll down to the next page. All right. So let's first talk about surjective maps. How to get it wrong. So consider a map F from A to B. And now let's say that that we want to say that F is surjective. So let's first do that. If we would use, let's see, sorry, the Curry-Howard interpretation to assert that F is surjective, to assert, let's see here, surjectivity, that it would look like so surjective means that for every element in the codomain in this B, there is an element in A that maps to it. So how would we write it down with Curry-Howard? It would say for every B in B, there is an A in A such that F of A equals B. Now, there's a little problem with this because it's too strong. So it captures something stronger because if F is quote unquote surjective in this way, then we actually get a map G from B to A, and we get a homotopy that says that F composed with G is homotopic to the identity function. How do you get such a map? Well, you can project out of the sigma type. So you can use the type theoretic principle of choice that we saw last week with Emily to swap the pi and the sigma. And then the first component of that sigma will be the type of this G, so functions from B to A. And the second component will say for every B and B, F of GB is equal to B. In other words, we have a homotopy from F composed G to the identity function. But in usually when we say that F is surjective, we don't mean that F comes equipped with a section. Okay, so in classical mathematics with the axiom of choice, there will exist such a section, but surjectivity itself is not expressing that. It's just the proposition that all the elements in the codomain are a value of the function. So what we see here is that that the Curry-Howard correspondence, or the Curry-Howard interpretation, is not appropriate to express surjectivity of a map. And this is very important to realize. And it doesn't really have anything to do with classical versus constructive mathematics. It's just it just comes from the fact that this pi sigma here doesn't really capture the correct concept of surjectivity. So we want to fix that, and in order to fix that, we should have some way of to say that for every element B in B, there is an unspecified element A in A that maps to B, but it shouldn't be part of the assertion that we can get hold of such an element A, because then we can construct our section. Okay. So this is where propositional truncation will come in, but let's first give another example before we start introducing the propositional truncation. So I'll just go to the next page. Anymore. And the second example is from counting and finiteness. So here we are. Yes. Let A be a type. And now to count the elements of A, what do we do when we are counting? Then what we're doing is to obtain a number n by establishing an equivalence from the standard finite set with n element. Equivalence. Oops, sorry, that goes off. Equivalence. Sorry for my handwriting. E from fin n to A. In other words, we define the type count of A. So this is the type of all countings of A to be a sigma type, n in n, and then an equivalence fin n to A. And the equivalence here is part of that sigma. So this is the way to bracket it. Now, if we stare at this, if we have such a counting of A defined in this way, then the type A, it will inherit by the equivalence from fin n to A, it will inherit a canonical ordering because the elements of fin n, you can think of them as the numbers 0 to n minus 1. They are ordered in a canonical way. And if we have an equivalence from fin n to A, then we can use that equivalence to also order the elements of A. So if we have such a counting of A, then we have established that A is an ordered finite type, linearly ordered finite type. And of course, that is stronger than being just finite. So we want to find a way to express that A is finite without imposing too much structure on A. And again, we will do this with the propositional truncation. So here you see how easy it is to get wrong if you just use sigma and pi. It's very easy to express a concept, but then actually you get too much structure if you use the Curry-Howard isomorphism. Some structure shouldn't be remembered. So here the countings should exist, but it shouldn't be part of the structure if you want to say that A is finite. So then we have to use a propositional truncation. So what we're going to try to learn here is to recognize when you have to use a propositional truncation. And also, of course, what is propositional truncation? Let's do one final example. So finally, we might want to oops, where am I? Express sorry, that that A is inhabited and to express that A is inhabited, it should just be the case that there is an element in A, but the element shouldn't be contributing to the structure of A in a way. So being inhabited should be a proposition, and just saying, okay, A comes equipped with an element, that is not a proposition. There can be uncountably many such elements. We would like that is in, oops, sorry, in A, oops, that went a little bit off screen, sorry, is a proposition. And this is the proposition that we're after when we're talking about propositional truncation. So the propositional truncation is going to express that the type is inhabited. For this purpose, we will introduce truncations. Okay. My handwriting in the notes on GitHub is a little bit better. I'm sorry. All right. So now we're gonna introduce the propositional truncations, and when you introduce something new in type theory, it's always a good habit to first characterize precisely the features of the thing that you're introducing, so that you already, in a way, hopefully uniquely characterize the kind of object that you're introducing. And one such a way to
Egbert,
yeah,
there's actually a pretty interesting question.
yes.
We're working in constructive mathematics, and generally we would like to have data around. So
Yes,
why would you want to
absolutely.
throw away the data of a particular equivalence? That seems counter to the principles of constructive math. And I think you might want to mention RP2 as an example in this answer.
Okay, so right. So I'm not saying that we are going to always throw away all the data. That would be very silly. But but sometimes but we do want to force things to be in a property. So for yeah, in this example where we were looking at the finite types, so you can also look at the types with 2 elements. This was what Astra was alluding to, and you can say that the type has 2 elements if it comes equipped with an equivalence from fin2 to A. But that is too strong again, because that one will say where true and false are going to, or 0 and 1 if we're working with fin n, and it says too much. So we kind of really just want to look at the type of types that have 2 elements, but maybe are not equipped with such an equivalence. And to do that, you use the propositional truncation to say, okay, there we want there to exist an equivalence, but we don't want this equivalence to be part of the structure. Right, so then there's the question, is this going to be somewhat non-constructive? Because because we all learned with Curry-Howard that in constructive logic, to prove an existential statement, you first give your element that you say satisfies the property, and then you prove for that element the property, so you know which one it was. But this is not necessary. Logic with propositional truncations is certainly still constructive. It just allows us to express more concepts. Is that an okay answer?
Sounds good. I just think I'd like to mention that when you actually take sort of the universe of 2-point sets, untruncating it would make it just contractible, but otherwise you get a model of RP infinity, which is a nice space that we'd like to study. And actually Egbert's work was on that. He invented that construction.
Yeah. Mm-hmm. Right. Right. So what goes on here is that, but okay, so I can kind of only say that to people who've seen categories and groupoids before. So if you would do it untruncated, like Astra says, you'll get a contractible groupoid, which isn't very interesting because it just has 1 point. But if you would look at the groupoid of 2-element sets, then that groupoid actually is not contractible. It has non-trivial isomorphisms, and those isomorphisms come from the non-trivial equivalences that exist on a 2-element set. And using the truncation, propositional truncation in your definition of the groupoid of 2-element sets, you actually capture that groupoid. I'm a bit sorry that I'm using the word groupoids here, but I think we are going to get there next lecture on Monday. Then I'm going to talk more about fin2. All right, so I think now I will move on to the universal property of the propositional truncation. So always before you introduce something, you specify, you give the specification of what you're about to introduce. And one way to give such a specification is by saying what the universal property is of propositional truncations. Well, I'm just gonna write it like this. So so let's say we have a type A. Let A be a type. And now let F be a map from A into P, where, sorry, where's my, here, where P is a proposition. And what I'm going to describe to you now is what it means for such a map F from A into a proposition P to satisfy the universal property of the propositional truncation. And then what we are going to do is we are going to assume that there is a propositional truncation, which will be a map of this kind that satisfies this universal property. But it's somehow good to set it up in some generality. Okay, so the idea is that well, let's just give the definition. So we say that F, so this F that we assumed here, is a propositional truncation. So this is the definition. It's the defined term is to be a propositional truncation. If it satisfies the following property, and this is the universal property of the propositional truncation. If the map that goes from P into another proposition Q, then we can precompose that with F. So this map we all know. If you start with the map from P to Q, then you can use F to obtain a map from A to Q. And if this map is an equivalence for all Q in prop. Oops, sorry. The R didn't appear. Let's see. There we go. Sorry, my tablet skills are not that good yet. So we say that F is a propositional truncation if this map is an equivalence for every proposition Q. Now, what does this mean? It means that in a way, if F here implies, if F implies, if A implies a proposition Q, then it must already be the case that P implies Q, and this is a way of saying that P is the best approximation among the propositions that has a map from A to P in it. Okay, so this is the universal property. So let's do some remarks. Okay. Remark. Okay. Why is the K not being written? Okay. So since Q is assumed to be a proposition, it follows. Oops, there's a W missing. And that's where are we? These two types, P arrow Q and A arrow Q, are also propositions. So this map that we have here above is an equivalence if and only if we have a map in the other direction. So, oh, sorry, how did that happen? So this map from A to Q to, sorry, from P, I wrote from P to Q to A to Q. This map is an equivalence. If and only if we have a map back that goes from A to Q to P to Q. So if we
There
want
was
to
a suggestion that you
yeah.
swap pre-composition and post-composition in the line above on the screen.
That I swap pre-composition and post.
Pre-composition and post-composition. Did you give the lambda term for what the map is explicitly?
This map here,
Yes. Oh, you must have said it. Then.
So this map is defined by precomposing with F. So if you have a map G here, then you get G composed with F from A to Q. And this map you always have if you assume F. And now we are just observing that this precomposition map is an equivalence if and only if we have a map in the other direction. So what does this mean in pictures? Let's draw a picture. If you have a map from A into Q, let's say this is G, and oops, here we have P, and on the side here we have F. It says that for every map G, there is even a unique map from P to Q that extends G along F. But because Q is a proposition, it just suffices for this thing to exist. So this here exists uniquely. Why does it exist uniquely if we have this equivalence? Well, because equivalences have contractible fibers, and the type of extensions of along F is a fiber, fiber of precomposing by F. Okay. So this is the universal property. So this is what we want to implement. But before we are going to implement it, let's prove that this universal property determines the propositional truncation uniquely if it exists. And then we are safe to assume it. Okay. So here is a proposition. How am I doing on time?
You are 36 minutes in.
Okay, thank you. Okay, so now let's consider two maps, F from A to P and F prime from A to P prime. Where P and P prime are propositions. Okay, and now consider also oops, the following three conditions. Let's say number one is that F is a propositional truncation. Oops. Two is that F prime is a propositional truncation, and 3. This one says that P is equivalent to P prime, and the claim is that if 2 out of 3 properties hold, then so does the third. Okay, so if, for example, if 1 and 3 both hold, then 2 must hold. That's the idea. Okay, so this here says that propositional truncations are going to be unique once they exist. So if we have 2 candidates to be a propositional truncation, so if we have f and f prime and properties 1 and 2 hold, then the p and p prime are going to be the same. So it shows a little bit more than uniqueness, but this is how we like it, how I like it. Okay, so proof. Let's first assume that 3 holds. So assume 3 holds, and we will show that then 1 holds if and only if 2 holds. So to do this, we say let Q be a proposition. And now we can draw a diagram. So we have the diagram with A arrow Q in it. Then we have a diagram with P arrow Q. Sorry, not the diagram, the thing in the diagram. P prime arrow Q. And we have here 3 maps. 1, 2, and 3. And here we have precomposing with F. Here we have precomposing with F prime. And here actually we have an equivalence, because precomposing by an equivalence is an equivalence, and we assumed that P and P prime are equivalent. So now, if you remember a while back, you proved the 342 property for equivalences, and now we can apply that to say that to see that this precomposing with F is an equivalence if and only if precomposing with F prime is an equivalence. Because if this one is an equivalence, then okay, this triangle commutes. Then the composite is this precomposing with F prime. That will be a composite of equivalences, and it's going to be an equivalence. And similarly, if this one is an equivalence, then by the 342 property, you can conclude that this this map here is going to be an equivalence.
There's an excellent question in chat. Why does the diagram commute? You need to know that in order to apply 2 out of 3.
Yes, you definitely need to know that the diagram commutes. Here in this case, it's because this Q is a proposition, and that means that this P prime arrow Q is a proposition. So all maps into it are going to be homotopic. So in the case here, it's really for a degenerate reason. Is that okay?
Yeah.
Cool. Okay, so this this proves that if 3 holds, then 1 holds if and only if 2 holds. So we have only one more thing to verify, and that is that if so if both 1 and 2 hold, how do we prove how do we prove that the tree holds? Well, we get this map from P to usually we took a Q here, but now we're going to take P prime. This is equivalent by property 1 to A arrow P prime, but we have a map here. We have F prime. So using this equivalence, we obtain a map from P to P prime. And similarly, we have also that P prime arrow P is equivalent to A arrow P, and this one is by property 2. And we have F here. So by using this equivalence, we get a map from P prime into P. So we have maps back and forth from P to P prime and from P prime to P. And since they're propositions, that will imply that they're equivalent. So this proves the remaining part. Are there any more questions about this?
Not at the moment.
Good. Okay. Then we're gonna finally introduce propositional truncations. Okay. And we're just gonna assume that they exist, because that's about as good as you get it anyway. So from now on, we assume as an axiom that for every type A, let's see, there is a proposition that we will call double vertical bars A. So this is the propositional truncation. It comes equipped with a map eta that goes from A into the propositional truncation, and this one is called the unit of the the unit of the propositional truncation, and then it satisfies this universal property, such that A arrow Q to A to Q is an equivalence for every proposition Q. Oops, sorry. Okay, and you can assume this as a higher inductive type, but since you saw this, or maybe will see this in Anders' lecture, actually I'm not going to do this, because actually all we are going to need about the propositional truncation is this universal property. It's kind of good to get used to universal properties, and this one is simple enough to get some practice. But also later, when you go further with your studies of homotopy type theory, you'll see that, especially in synthetic homotopy theory, you can do a lot with just universal properties. So it's good practice to work just with them. So let's give it a go. Okay, so let's first use prove a little lemma. And lemma. So oops, what is that? I pushed some buttons on my pen. Okay, sorry. Let f be a map from A to B. And then we obtain a map that we will call like this. And it goes from the propositional truncation of A to the propositional truncation of B. Okay, maybe it will be fun to try to prove this together. So proof using the universal property. So I'm gonna have a look in the chat, and maybe if you guys have suggestions to do this, then I'll try to follow. People are talking about two-level type theories. Oh my god. Okay, does anyone have a suggestion? Which universal property do we want to use? I guess I guess the chat just went off topic. Anyway, it doesn't matter.
Use two-level type theory. I'm just kidding.
Yeah, I think that seems to be the suggestion here, to fire up ACTA with strict sets and whatnot. But no, that's not necessary. So we want to use the universal property of A. That's the answer. So we want to use this equivalence from A into B. This type of functions is equivalent to the type of functions from A into B. And here we have a map, because we have first F, and then we can pre-compose it with eta. And eta, if you recall, is this map from B going to B, to the truncation of B. So here we have this map. And then using this equivalence, we obtain uniquely a map from the propositional truncation of A to B. Why is Amy shaming people?
For going off topic.
I guess I should just close the chat and let you guys have fun.
Yeah, don't worry about it. Yeah.
People
were asking about like set truncation. That's how we ended up on two-level type theory.
Oh yeah.
Yeah.
Yeah, set truncation is a good one too. I don't think we are going to get there in these 3 last lectures, but there in the book you can read about them by yourself. So you will have all the technical tools that you will need to understand that.
There's one question / suggestion in the chat, though. You might want to take a look at that.
Okay, sorry, I'm not seeing the chat anymore, but can you ask the question?
Sure. Are they equivalent because of the universal property, the first line of the proof?
Yeah, these are equivalent by the universal property of A. So let's go back to this universal property. See, when you have the universal property of the propositional truncation of A, they are on the left of these arrows, and it says to map into another proposition Q, you can map from A into Q. And now we're doing that where we take Q to be the propositional truncation of B, which is a proposition. So this one is an instance of the general universal property of the propositional truncation of A. Yeah. Okay. And there's a corollary of this lemma also. So corollary, if A is equivalent to B, then the propositional truncation of A is going to be equivalent to the propositional truncation of B. And that's just because if they're equivalent, then we have maps back and forth. But then by the previous lemma, we'll get maps back and forth here. And that's enough for propositions to be equivalent. So this even holds when when A, oops, that's not a very good arrow like this. When A holds if and only if B. And this here sometimes is called co-inhabited. So if you have two functions back and forth, then the propositional truncations will be equivalent. Okay. So now we have some tools, the propositional truncation, to reinterpret logic into type theory in a way that interprets propositions as propositions. So Curry-Howard interpreted propositions as types, and now we are going to interpret propositions as propositions. And I'm going to motivate that a little bit. So recall that if P and Q are propositions, then P plus Q is a proposition. Hold your breath because this is not true. If and only if whenever P holds, Q must be false. So what I'm saying here is that, okay, under some conditions, this coproduct P plus Q will be a proposition, but it's not always going to be true. It's only going to be true under this condition. But let's for fun try to prove this. So suppose let's just prove the direction from here to show that P plus Q is a proposition. So if you want to prove that P plus Q is a proposition, we want to show that all the elements are equal. And you do that by pattern matching. So we have some cases in left of little p equals in left of little q. And then we have in left of p equals in right of sorry, what am I doing? So the in rights are q's, and now I have to find my eraser. Does this work? Yes, good. In left of p prime. So I'm writing here the four cases that we need to address. Not I'm not making any statements. In right of q equals in left of p. Oops. And the last one is in right of q equals in right of q prime. So if we want to prove that all elements of p plus q are equal, we have to prove these four statements by pattern matching. So why is this one true? This one is true because p equals p prime in p, and that's because p is a proposition. Now this one is, you can prove this because we can derive falsehood. We have p in p and q in q, but also P arrow not Q. So together we have a contradiction, and then this equality follows from X also. And the same reason is here. So this one is the same. And here it is again because Q equals Q prime in Q. So under this hypothesis, it follows that P plus Q is a proposition, but it's certainly not always going to be the case. So if P and Q are both true propositions, then P plus Q is going to be equivalent to the Booleans, which is a two-element type, and that's not going to be a proposition. Okay. But we still want to interpret disjunction into type theory, and disjunction should be a proposition. So so now we make a definition. Define P or Q to be the propositional truncation of P plus Q. So this is now our definition. We say, okay, it's all right that P plus Q wasn't a proposition. We're just gonna propositionally truncate that type and define this to be our disjunction. And to see that this makes sense, we have to prove a lemma. We have to prove the intro and elim rules. Sorry, mostly the correct elim rule for P or Q. And so the lemma is going to say that if we have P or Q and we want to show that this implies R, well, that happens if and only if P implies R. And did I write the Blackboard bold R? Oh my God. Let's write a normal R. I guess it's just from the way I write my R's. Q to R. Okay. So why is this this true? So this equivalence here, you can say it's the universal property of the disjunction. So the universal property of the disjunction should say how to map out of a disjunction. And to map out of a disjunction, what you do is you map out of P and you map out of Q. And then you know that P or Q implies R. So let's try to prove this. P or Q implies R. By definition, this is P plus Q to R, but we assume that R is a proposition. So by the universal property of propositional truncation, we now know that this is the same as P plus Q into R. And maybe in the last lecture in the exercise, I'm not sure precisely which one you did, but the universal property of the coproduct is that this is equivalent to P going into R cross Q going into R. So this this is something that that you can show with this last step with function extensionality. So in section 13, there's an exercise about that one. Are there any questions about this junction? I even wrote down which exercise it is. 13.8. If you wanna make that one. Okay, so this is our definition of disjunction. And now we can hold a similar story about the existential quantification. Remember when we talked about surjective maps in the beginning, we used sigma to express an existential, and then it was too strong. So now we are going to fix that. Let's say here are my notes. Here we are. Consider P from A into prop. So P is a family of propositions over A. This is also the definition of a subtype of A. If you remember that from Emily's lecture about the truncation levels. Okay. Then okay, so then my notes say that sigma x in a p of x is a proposition if and only if for every x, y in A, if P of X holds, and if P of Y holds, then X must be Y. Okay, so here again, similar to the case with the disjunction, the message is, okay, sometimes this sigma is a proposition, but more often than not, it's not going to be a proposition. This condition just won't always hold. But we can at least, I'll leave this as an exercise here, and you can look up the notes on the GitHub. The answer will be there. But okay, if we take this for granted, then we say, okay, the sigma type is very often not a proposition. What are we going to do to express the existential quantification, which we want to be a proposition, because in usual mathematics it is a proposition. So we make a definition. Let's just scroll down a little bit. So we still have our A and P. So we define the existential quantification P of X to be sigma X in A, P of X propositionally truncated. So we kind of acknowledge here that sigma type was an okay existential quantification. The only thing that was wrong with it was that it's not always a proposition, so we're just gonna propositionally truncate it. Then we have to prove that this satisfies the correct lim rule for existential quantification. So we prove a lemma, and the lemma is again of the same form. If we have and exists X in A, P of X, and oops, here, and we want to prove that some property R holds. Well, to do that, it's equivalent to show for every X in A, if P of X holds, then R. And the parentheses are here. Okay, and again, this proof is just a chain of equivalences. So let's do it. So existential A P of X implies R. This here is by definition it's by definition sigma X in A P of X going into R. By the universal property of the propositional truncation, this is equivalent to sigma X in A P of X going into R. Now the parentheses are here. But Emily showed in class last time that this is equivalent to, for every X in A, P of X arrow R. So if we define the existential quantification in this way, it satisfies the correct limb rule. And now we can write this table of how to interpret logical connectives into type theory. Logical connective, and then type theory. So what are the logical connectives? We have one, sorry, we don't have one. We have true, false. We have P arrow, sorry, double arrow, Q, conjunction, the disjunction, and if I don't miss them. Oh, I wrote such an ugly implication sign. Let's do a better one. Okay. We also have P if and only if Q. We have exists X in a P of X, and we have for all X in a P of X. So this table is going to tell us how to interpret each of these. And the interpretation of truth is just a unit type. The interpretation of falsehood is the empty type. Then this will be the type of functions from P to Q. The conjunction is just the Cartesian product. So you can still show that this is a proposition if P and Q are propositions. This will be the propositional truncation of the coproduct, like we saw. So this one will just be P arrow Q times Q arrow P. This existential quantification will be the propositional truncation of the sigma. And for all is just pi. X. So we saw in Emily's lecture last time that products of propositions are propositions. So this is a new interpretation of logic into type theory, and we changed two things, namely how to interpret disjunction and how to interpret existential quantification. And that was to ensure that that the disjunction is a proposition and that the existential quantification is a proposition. Are there any questions?
So for the by implication, you could have also written P is equivalent to Q, right?
Yeah, absolutely. Yeah, maybe I should have. That's right. Okay, I have 20 minutes left and I have 5 minutes per page on my notes, so let's move on. So now let's use what we just defined to talk about the image of a map. So let's say definition. Let F go from A to B. Define the image of F to be sigma B in B. And then we propositionally truncate the fibers of F at B. And why am I propositionally truncating the fibers? Let's suppose that we didn't do that. So let's suppose we wrote sigma B in B, and then just straight up the fiber of f at b. Okay, so this, if we unfold the definition, b and b, the fiber is the sigma type, sigma a in a, f of a equals b. Okay, so now things are going to go wrong because we can swap the sigmas, sigma b and b. Now f of a equals b, and we recognize from Ulrich's lecture that this part here is contractible. So what we get then is that this is equivalent to a, and this is an unhappy face. If we made the wrong definition, then we ended up with the definition of image that is equivalent to the domain of the map. We don't want that. So here, propositional truncation really saves the day. If we didn't do that, we just we got so wrong if we forgot to propositionally truncate. So sometimes you have to be aware that you propositionally truncate. So is there anything we can show about this? Yes. So now let's also define, okay. Let's also then define a map Q of f that goes from A into the image of f. And let's define a map I of f that goes from the image of f into B. And how do we define this? We say Q of f at A. Well, the first is going to be a pair, and the first component is going to be something in B. That's going to be f of A. And now something in the propositional truncation of the fiber. So it's going to be the unit of something, and we take the pair A raffle. So this is our definition of Q, and the definition of I of f is just the first projection. So the image is a sigma over B, so we can first project, and that's our definition of I. Now this this I of f, because the image, let's go back to the definition, oops, is a sigma over propositions. The projection out of this the sigma type is always going to be an embedding. So this is a note. I'm not gonna prove this. Note I of f is an embedding. But more interestingly to us is that this Q of f is surjective. So I need to tell you now how to define surjective, but you can all guess now how to define what it means for a map to be surjective. So if you want, you can write in chat what you think how to define surjectivity. So let's f from A to B, then f, oops, I need to, did the two-level type theory just kill the chat? Because nothing's going on anymore. Then f is surjective. So how do we define this surjective of f? Oh, here I should write if we have an element of this type. Any suggestions? Yes, finally. I was hoping someone would say the right thing. Yeah. Okay. So F is surjective if the fibers of F are all inhabited. So let's try to show. We have this claim now that Q of F is surjective. So the map into the image is a surjective map. Let's try to prove that claim. Okay. So we have to prove that for every element in the image. So for every, to show Q of F that goes from A to image of F is surjective. Oops. Let's so we need to assume something in the image. So we assume a B in B, and we assume an X in this truncated fiber. Fib F of, what did we say, B? And we want to show that something is in the fiber of Q of F at the pair B, X. That's what we want to show. Now, since the fiber of F at B is merely inhabited, we can use the universal property. So we have fib F of B arrow, fib Q of F at B, X, that this here is equivalent to fib F at B arrow fib Q of F B, X. Yes. There it needs to be. Oops. And if we want to construct an element of this type, note that we have assumed that there is an element here. So if we have such a function, then we can use this element X and apply the function to that X to obtain an element here. So we are going to construct this function by the universal property by constructing a function here. And here we can now say, let A be an A, P from F of A equals B. So we, in other words, we assume something is in the fiber. Now we can say path induction on P because this this B is a free endpoint. So it suffices to show that we have an element in fib Q of F, and we did path induction, so this will be F of A, comma, and this X here is now the pair AP, which is A raffle, so this is eta A raffle. So it suffices to prove this, but notice now that this here is exactly Q of F at A. So we are looking in the fiber of Q of F of a value at Q of S, and of course there is something in there. So here it is done. So this shows that Q of F is surjective. Okay. And the last thing I want to talk about in the next 10 minutes, I think. Yeah, I have 10 minutes left. Is about the finite types again. Okay, So here again, we can now make a definition. We say that A is finite if we have elements of type, and this type is called is finite of A, which is defined to be the propositional truncation of sigma n in n, and then fin n is equivalent to A. So we say that A is finite if there exists a natural number with an equivalence from fin n to A. And this, of course, is a proposition. So that's good. So here now we resolved this issue that if we had the actual equivalence, then we were ordering A. Now we don't have this this equivalence, so we're not ordering A. We're just expressing the property that A is finite. So now we can also define. Oops, sorry, I don't have my pen under control. Define F, the type of all finite types, to be sigma x in U, let's say U0, such that is finite x. And similarly, we can also define types that I'm going to call BSN here. And this type is defined to be sigma x in U0, but now not there exists an n, because we already have been given the n, but just a propositionally truncated equivalence from fin n to A. And in the book, I wrote Blackboard bold Fn for this. But this is the standard notation for the field with n elements in mathematics. So I actually am going to change this, and I prefer this notation. And why is it called BSN? It's because this will follow from univalence next time on Monday, that the loop space of this type, or the type of identifications from fin n to fin n in this BSN, is going to be the type of all permutations on fin n. So that's a symmetric group on n elements. And B is then a common letter to be used if the loop space of a type is a certain group. Okay, so maybe one last example to finish today's lecture. To show that, just to show a little lemma, if A and B are finite, then A plus B is finite. So this will be the last thing. If I write small enough, then it can fit on this page. Proof. So notice that that we're proving a proposition now, that A plus B is finite, and we have, let's say, H from is finite A, and K of type is finite B. So now we are going to use that these are defined as propositional truncations, and we're proving a property. So then we may assume, so by the universal property, we may assume an n in n and an equivalence E from fin n to A. So this is if we apply the universal property of the propositional truncation here. And we may also assume another number m and f from fin m to b. Okay, but now observe. Now we can now finish the proof by showing that fin n plus m is equivalent to a plus b. And if I erase this, if I move this to the side for a bit, oops. You can easily prove by induction that this thing is fin n plus fin m. Oops, missed the letter. And that is equivalent to a plus b. So this equivalence here is constructed by induction on probably on m, I would say. And once you're here, you just apply that that coproducts preserve equivalences to get an equivalence to a plus b. But now we have an actual equivalence from fin n plus m to a plus b. So all we gotta do is to take eta of n plus m, and then that equivalence that we just constructed, let's call it alpha for the moment. And this is the proof that a plus b is finite. So I'll stop here. Thank you all for coming today, and see you on Friday in Anders' cubicle HoTT lecture.
Yes, thank you very much, Egbert. And I promise the chat was talking about your lecture most of the time. You dropped in at the worst moments.
Just not when I was speaking.
Yeah, exactly.
Of course, I believe you.
Yeah. Right. So as Egbert said, yeah, on Friday we have Anders' second lecture on cubical AGDA. Tomorrow on Thursday we have some problem solving sessions, and you're definitely going to want to be here on Monday for Egbert's second lecture on univalence.
Yeah.
So we got there.
Finally.
Right. So let's see. There were some interesting questions or some interesting discussion in the chat toward the end about cardinality of finite types. Maybe does someone have a specific question, or do you want to just say something about that?
Okay, so yeah, I was actually planning to say that, but I was a little bit short on time. So the cardinality of a finite type is, of course, that natural number that you can construct, but here in the definition, it is truncated away. What you can have an alternative definition of is finite. Let's just write it down. Here is finite prime of A. And this one says sigma n in n, and then there's such an equivalence fin n to A. And and this also is a proposition. And actually, these propositions are equivalent. And the reason that this is a proposition is that if A is finite, then of course there's going to be at most one natural number such that that natural number is the cardinality of A. It's not going to have two different cardinalities. So I was not going to go into the proof of that, because that actually is kind of a really technical argument to make it precise, at least to a level that Agda is happy. But yeah, you can show that if that fin n and fin m, if they are equivalent, then n and m must be the same natural number. So that's what goes into that proof. Yeah.
Have you formalized the equivalence between these types in Agda?
Yeah, of course.
Oh, in which case, can you actually post that on Discord? I think a few of us would be interested in looking at it.
Yeah, I'll post it after the lecture in general or in HoTT lectures. What's better?
Either.
Okay, I'll post it in general. Any other questions?
Thanks for the lecture.
Yeah, thanks for coming.
All right, we'll stop the recording.